All right, next up, Chapter 8, First Order Logic. Okay, so Chapter 8 is all about learning about a more expressive type of logic than propositional logic. And Section 8.1 starts us off with discussing representing knowledge and talking about some of the shortcomings that different languages have in representing knowledge, and tries to set up the motivation for another type of logic that is going to be more flexible. It's going to be more useful. It's going to be more expressive. So chapter 7, what did we do? We learned how to represent knowledge by using a type of logic. And we also learned how an agent could figure out what it should do based off of the knowledge that it has, using those representation tools. Okay, so chapter 8, representation revisited, that's the first section. Then they're going to talk about syntax and semantics of first order logic, how you write it and what the different things mean. Going to talk a little bit about how you can use first order logic, and then at the end, you're going to talk about knowledge engineering, the process you go through to create an expert system, really. And that'll be your next and last major programming project, will be to create an expert system using Prolog. All right, so section 8.1, as I was saying, it's the textbook doing its best to explain why we need a more expressive type of logic. Okay, so you can talk about different types of formal programming languages like Java, C++, Python, Lisp. Okay, now what these languages tend to do is, if you think about it, they're representing certain computational processes. What do we mean by that? You're assigning data to certain variables, you're moving data into different registers, you're moving stuff around in memory, that sort of thing, doing arithmetic. Okay, fine, right? And, this is the core of what they're doing, and the amount of knowledge that programs based on these languages can represent, or how they represent them is, and how they manipulate them, is kind of limited, okay? So you talk about, having a tic-tac-toe game, for example, right? So you can imagine having a data structure like a 3x3 array. And so you assign an X to, 0, 0 in that array. Okay, fine, that's a fact. That's a fact. There's now an X in that square. Or think about Wumpus World. You got a 4x4 array. And, you can look at a statement, it's in pseudocode, looks kind of like this. It's easy to see that, well, we're saying that there's a pit in square 4, 4. Okay, fine. Those types of formal languages can support that. Okay, we can make that work. But what they're missing is a way to create new facts based off of these existing facts, right? So you can take certain pieces of information and say, yeah, there's a pit there, there's an X there, fine. But what if we need to infer? What if we need to deduce? What if we need to, do some kind of entailment with those languages, right? Or with Java, C++. They're really kind of missing a way of doing that. Those aren't the tools that you would need to do logic programming necessarily. Okay? Even if you could write some code that would enable you to derive some kind of new fact from existing facts, right? Which you can do to a certain extent. The problem is that that process is, you can imagine there being a function that was written to do it, right? Or some kind of method or procedure, fine, whatever. But that code is written by the programmer in the context of that program. And so that process of entailment, or of deducing a new fact or deriving a new fact, it's going to be limited to that context, to that domain, right? So it'll work great for that program, but not necessarily for another program, right? So all of those details are limited by, how that would work are limited by the programmer's knowledge and the program in which, it's being, that code's being written, right? You're kind of stuck within this one domain. We can contrast that with How propositional logic works, right? In propositional logic, we saw that knowledge and inference, those are separate things, right? There were rules for inference that it didn't matter the domain, it didn't matter the context. We had knowledge that we could represent using propositional language, but there was a procedure for deducing your new facts, for doing your entailment, that was completely independent, right? It worked a certain way. It didn't matter what the knowledge. The inference part, completely domain independent in propositional logic. Now, another limitation with data structures in formal languages like Java, C++, is that they have a problem with connecting information. For example, that it's hard for you to express a piece of information like, well, there's a pit in square 2, or in 3, 1, right? Or it's hard to have in an array, right? Or within the syntax of a particular formal language like C++, Java, etc. If there's a wumpus in square 1, 1, then it's not in 2, 2, right? So that type of limitation is problematic, right? And so we're going to need something else. You can assign, a piece of information to a variable, but it's hard in those programs to be able to deal with incomplete information, or within those languages, incomplete information. If it's in 2, 2 or 3, 1. If the wumpus is in 1, 1, it's not in 2, 2. Okay. Propositional logic is a different type of language. Okay. And it's a language that can handle these problems. It's a declarative language, right? And so the reason that it can handle these problems is because the semantics, what the different sentences mean, are based off of truth and how it's related, how that truth is related between the sentences that are written in that language and all of the different possible worlds, okay, that they could be describing. Propositional logic also is expressive enough to deal with partial information, right? The tools in the language, tools of disjunction, negation, right? They can help with dealing with partially unknown data. Now, there's another thing that is really useful with propositional logic and other types of logics is this idea of compositionality. Okay, so what this means is that the sentences in languages that have this characteristic, the meaning of those sentences is based off of the meaning of all of the parts of the sentence. Okay, so if you take S sub 1.4 and S sub 1.2, right? This right here, the whole meaning of this sentence, you understand the meaning because of its individual parts, S14, S12, right? So with this sentence, with the conjunction, what that's saying is there's a stench in 1.4 and there's a stench in 1.2. And it's natural, right? It's a natural expression. It makes sense, right? Because if you just look at S14, well, it means stench, 1.4. S12, stench, 1.2. We'll combine them together. It means there's a stench in both of them. Fine. It flows. It's easy to see what it means. S14 and S12 doesn't have a completely separate alien meaning that is divorced from the meaning of its parts, right? You don't say, well, S14 means there's a stench in S14, and S12 means there's a stench in square 1.2, and then have the and part mean something completely else. They're completely separate. Nope, those Sharks suck because they can't win the Stanley Cup, right? It doesn't have a completely separate meaning like that. Okay, so propositional logic has that kind of strength that the formal languages like Java and C++ don't. Now, there's a problem with propositional logic, though, in that it's very repetitive, right? It's not very concise. So, for example, if you want to say, remember from the previous chapter, if you want to say, for example, that you want to set out a rule that says if there's a breeze in square 1 1, right? There's going to be a breeze in square 1 1 if and only if there's a pit in 1 2 or a pit in 2 1. That's one rule that you have to include, one sentence that describes one fact that you have to include for one square. Right? You would have to state for every single square, you'd have to have a repetition of this sentence, right? To have a complete description of what it means to have breezes, right? You'd have to have an entry for B1 sub 2, B sub 1 2, B sub 1 3, B sub 1 4, and so on. You'd have to have a sentence describing what it means to have a breeze for every one of those squares. That sucks, right? It'd be a lot better just to be able to say, hey, if you've got a square next to a pit, that square is going to be breezy. You got one sentence, one phrase in this case, that covers all of the cases. It's a lot more concise. Now, why was that last sentence, that last phrase, why was that so nice? Because it was based off of natural language. It was English, right? And such languages, incredibly expressive, right? We use those languages all the time. English, Spanish, Italian, whatever. Those languages have evolved over thousands and thousands of years, right? To be as expressive as they are. It's interesting because linguistics and philosophy, for most of their history, have thought of natural languages like English, Spanish, Italian, whatever, as declarative, representational languages, right? So in the past, they've been thought of that way. Now, the way they've been thought of now, in modern times, it's kind of changed a little bit, right? In that natural languages are being used for communication more so than representation, right? So humans are using language to communicate instead of representing just arbitrary facts, or maybe not so arbitrary facts, right? So, for example, if someone yells to you, "Look," right? That's not a fact that's being represented. That's telling you to do something. It's a command, right? We're not talking about the state of, how many Oreos you have, right? Or that there's an X in a particular square. It's a command. It's telling you to do something, or it's telling you to look over there, or that there's something that you have to be aware of, right? So the meaning of a word, for a human to deduce what it means, there's context there that you have to take into consideration. So if you just had the word "look" in some kind of knowledge base, it'd be useless. Without context, look on by itself doesn't really mean anything. And so, depending on the context in which you use a word could have completely different meaning. So what does that mean? Well, natural language by itself is problematic because natural language is ambiguous. It's inherently ambiguous. And so this is a big time problem when you have representational languages or for representational languages. For example, context, right? If I was to talk to another person, I say, "Spring, oh, it's so nice." Right? Most people instinctively think of spring as the season. Flowers are blooming, birds are chirping, bees are buzzing, right? So most people don't think about that thing that goes boing, right? They're not thinking about, springs, metals, piece of hardware. They're thinking about the season. So which did I mean? Well, you're not going to know really unless there's context. Now, if I hand you a spring and I say, "Hey, take a look at this spring," if I actually hand you the piece of hardware, it's going to have a completely different meaning. Now, here's why I'm so jealous or so envious of people who are bilingual, right? Some of my students have heard me say this in other classes and talked about these studies that have been done that people who are bilingual are just naturally better thinkers than people who are, monolingual. It's because of this right here. The understanding of the world is strongly influenced by languages that we speak. People who can speak in different languages have different ways of expressing different ideas, different thoughts, different concepts than the rest of us, right? If all I can do is speak English all I can do is express ideas in ways that are allowed by English. But if I could speak English, Spanish, and Italian, I have a broader toolbox for expressing different ideas. Why? Well, there's been experiments that have been done, and those experiments tend to show that people internally in their brain, the way their internal thought process works, is that the words themselves are forming a nonverbal representation of the world. And so words can behave as these sort of anchor points that help us to form our perceptions of the world. And the interesting thing is that different cultures who speak different languages, they're using words to represent things in different ways. Okay? And so the ways in which people communicate, use their language, the different languages that they speak, that allows us to have a better idea of how those different cultures think, approach the world, make their decisions. So you can express ideas in different ways and have either less concise or more concise communication of those ideas or understanding of those ideas, right? And you can express an idea in a couple different ways, and one way might be easier to see than another. And depending on how you express a particular idea, it might be easier to derive some new fact or some new insight or some new knowledge more easily than if you had expressed that idea in some other way, right? So in first order logic, if we have conjunctive normal form, if we write some sentence according to that form, it's really easy for us to see that not A or B is the same as not A and not B, right? Now we could rewrite that using some of the logical equivalencies that make it harder to see what's going on, okay? Or make it harder to understand what's being communicated. Now, can the same be done with the human brain and with the human thought process? For the longest time it was thought no, but now research is seeming to suggest that maybe the human brain does in fact work like this in a more natural way than we might have thought. Well, it turns out people who were studying this, researchers, were able to train a computer, an artificial intelligence, to predict things about images people were given using brain scans, right? So basically how the brain worked and how different parts of the brain lit up, the AI was able to determine a certain percentage of the time what image the person had seen, right? Because the human brain was using natural language as a form of nonverbal representation of ideas. So what's the point, right? And I already kind of alluded to this earlier. In formal logic, you can represent knowledge different ways, okay? And it may make no difference, or it may make all the difference in the world, right? Now, the knowledge itself can be represented, can be understood, and represented in different ways. I can say, let me give you an example, right? I can say hi, I can say hola. Two different ways to represent the same idea, right? Both are greeting, fine, might make no difference. But one representation could make it easier, could make it more efficient, right, to derive new information than the other. I mean, to put it another way, right, in formal logic, how you represent the information doesn't make any difference, okay? There's always logical equivalencies that you can make to represent knowledge in a whole bunch of different ways, okay? But depending on how you represent them, okay, that could lead to derivations that take fewer steps. The proof might be able to be done with fewer intermediate steps, thereby enabling, your AI to decide what to do faster, have it take less time. Could also mean that if you've got an AI running on a particular machine that has very limited resources, hardware, memory, CPU power, whatever, there may be certain ways that you represent knowledge that lead to techniques of derivation that are possible on that limited hardware, as opposed to other ways of representing that knowledge, which would lead to types of derivations that are not possible given that hardware. Now, there's certain types of non-deductive tasks, such as learning based off of the agent's experiences, that are necessarily, the outcomes there are necessarily based on the representations used. So the representations there definitely are going to matter. Now, later chapters, which we're not going to get to, shows, I think it's chapter 18, that there could be a couple different possible theories of the world, its understanding of the world. And so there might need to be a way, or need to be a way, to break ties, which one's better. And as it turns out, what's most succinct, which takes the least amount of heavy lifting by the logic language, that's going to be the winner, right? So it turns out how a language influences thought, how you're going to represent ideas, very, 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 very important to intelligent agents. And it's going to be very important to how quickly and how efficiently they can learn things, and whether or not they are going to need to learn things in one way or another. So we want to be able to combine, we want to be able to borrow the best aspects of formal languages and the best aspects of natural languages. Okay? And so if you can do that, then you're going to get a better overall language, right? So you're trying to combine the best of both of those types of languages, propositional language, natural language, and you want to minimize the worst parts, right? You want the best of both worlds, but you want to cut out the worst. So consider what natural languages have, right? Natural languages like English, Italian, Spanish, whatever, you have noun phrases, okay? And so we can say that these refer to objects in an environment or in a domain, squares, pits, wumpuses, okay? Natural languages have verbs, they have verb phrases, and those things can be used to help with relations between objects, right? One object shoots another object. One object is next to another object. One object is breezy, okay? And natural language also has functions, right, where you can use verbs that are going to help you describe some kind of inputs and outputs for different types of relations, right? So these are elements that we would like to have in a language that we can borrow from a natural language to make our new logic language more expressive, okay, more powerful. Okay, so let me give you some examples of these entities. Objects, people, houses, numbers, cars, money, whatever, right? Relations, right? So these are often referred to as properties if you're talking about a unary relation. So things like red, bogus, prime, blue, some property of something you could describe, an object. Think about, variables for an object in C++ or Java or something. A two-door car, for example. You could also have n-ary relations, brother of, boss of, owns, pet of, stuff like that. Functions, the father of something, I'm your best friend, more than that, less than that, right? So you could take that a step further and you could consider any kind of assertion of fact can be referring to objects, properties, relations, some combination of the two, or three, or whatever. So some examples. 8 times 3 equals 24. Right, so what are the objects there? 3, 8, 24, times, equals. Right, what are relations? Equals, what's the functions? Time, times, right? Climate change causes the sixth mass extinction in 2010. What are your objects? Climate change, 2010, mass extinction. Relation, began. Properties, sixth. Right? So, just some examples of those assertions. Now, first order logic, which is what we're going to start actually digging into in section 8.2, it's built on objects and relations. Okay? And so, it's powerful enough and expressive enough that you can express all kinds of facts about any combination of objects in the universe. Some objects, all objects, it's anywhere in between, right? So, because of its expressive power and its ability to describe the world using elements of natural language and propositional logic, which we just studied in chapter 7, it's useful all over the place. AI, philosophy, mathematics, whatever. Okay, now the assumptions of reality, right? The ontological commitment, it's called. The assumptions regarding reality that propositional logic makes and that first order logic makes, that's what sets them apart from each other. We're able to express by using models regarding truth sentences that you can write, right? So propositional logic assumes that facts are going to be true or not in the real world, right? Now first order logic is going to add this idea of relations, and those relations are going to hold or they're not going to hold, right? So whether a fact is true or not, whether it's true or false, is quite a bit simpler, much less complex than whether or not certain relations are going to hold up. Different types of logics, you can tell the difference between them. They're epistemological commitments, as it's often referred to, right? So, for example, propositional logic and first order logics, sentences in those logics, there's some fact that you're trying to represent, okay? And that fact, as far as the agent's concerned, could be true, could be false, or the agent doesn't know, right? So what you have is three possible states in those logic, right? In those logics, true, false, unknown. Now, you have other types of systems or other types of logics that use probability theory. And what they do is they allow you to specify a percentage of belief, right? Somewhere between 0 and 1. 0, total disbelief. Oh, that's absolutely false. I don't believe that at all. Or 1, I'm 100% sure that that's true. So, for example, there's a 75% chance there's an enemy behind that door. There's a 33% chance that, if I eat that food, I'll be poisoned. There's a 16% chance that I'll do blah. Okay, so probability theory is allowing for, degrees of belief. So in those types of logical systems. In propositional and first order logic, it's true, false, unknown. I know it, I know it's true, I know it's false, or I don't know at all, right? That's different than a logic system that's using probability theory. Okay, so we're finishing up here, and here's a summary of different logics, right? And we didn't cover all of them, I only talked about a few of them here, but if you've got a propositional logic, what's its ontological commitment about what exists in the world, right? What do you have? Facts. Okay, what can you say about those facts? True, false, unknown. First order logic. You've got what exists in the world, facts, objects, or relations. Okay, what can you say about the world that you believe about those facts? True, false, or unknown. Okay, temporal logic includes time. That's another thing that you can say about what belongs in that world. Probability theory's got facts. You got a degree of belief that falls in between 0 and 1. And then you've got another type of logic that, given some of these we're not going into in this chapter certainly, facts that have a degree of truth. Okay, and they have, what an agent believes about those facts is some kind of an interval of value. But again, the point of this table here is just say, look, there's different types of logics, there's different things they can say about what exists in the world, and there's different things that they can believe about those things they're saying in the world, okay? So, similar to how, if you're a physics student, math, you better be comfortable with with math. Even though you're not a math major, you're a physics major, you have to have a certain degree of comfort with math and able to do physics. And so, in a similar way, an AI student, even though you're not a philosophy major, even though you're not a logic major, even though you're not considering yourself a logician, you have to be comfortable with being able to work with logic to a certain extent, right? So, that's what we're covering, and that's, in case you're wondering, well, what's the motivation? What the hell? Why do I care about different logic and what's true and what's not, and what's a fact and what's a relation? Who the hell cares, right? But if you're going to make a knowledge-based agent, right? If you're going to make an agent that's going to be able to have certain facts about the world and then come up with what it's supposed to do, if it's going to be able to deduce what it needs to do, then you have to know how to represent knowledge, and you have to know how logical deduction works, so that way you can program it or choose an appropriate language to help you to program it. Okay, so that's section 8.1. Really fast, really quick, really sweet. Basically, as I was saying at the very beginning, just this section is trying to say, here's why we need a new language, right? We have propositional language, which is useful but not as expressive as it needs to be. We have natural language, which has all the expressiveness that you could ever want, but it has inherent ambiguity. Talk about programming languages like Java, C++, that are limited in their ability to deduce new facts. We also compared and contrast briefly, very briefly, different types of logics, right? So when we come back in the next section, we'll start digging into the first order logic, the basic syntax and semantics of it. And as we go forward, you're going to see, especially if you've been looking at the prologue tutorials already, that there's a lot in common, right? It's going to feel pretty natural, I think, for you to transition into using prologue once you get through this chapter, and certainly once we get through chapter 9.